Hi there, my name is Dimitris Haralambidis, and on this video, we will see how we can expand our knowledge on finding trigonometric ratios of more angles, and more specifically of angles which are greater than 360 degrees and later on than 2 pi radians. And we will see the whole process through a guided inquiry I have created. So let's begin with it. We need to draw each of the following angles: an angle of 30, an angle of 390, and an angle of 750 degrees, respectively. I will use three different colors for that. 30 degrees. Remember that when we are given a unit circle, every single angle is drawn by starting its first side lying on the positive horizontal direction and then moving in an anti-clockwise manner. We move up until the point where we would have drawn the full size of this angle. So we are looking for an angle of 30 degrees. Let's say that approximately it should be there. Then let's change to green. For the angle of 390 degrees, once again, I will begin from here and moving in an anti-clockwise way. I need to now draw an angle of 390. So I'm going to draw a full circle, which stands for 360 degrees, plus 30 more, and the second side will be somewhere there. Finally, for the angle of 750 degrees, I will once again begin from here and then moving in an anti-clockwise manner, as always. I should draw firstly 360, then another 360, which takes me to 720, and then an extra 30, which takes me to 750 degrees. Now, we are asked to clearly label the endpoint at which the second side of each angle intersects with the unit circle. And we should name these endpoints as A, B, and C respectively. So let A be the point where the second side of the angle of 30 degrees cuts the unit circle. Let B be the point at where the second side of the angle of 390 degrees cuts the unit circle. And finally, let C be the point at which the second side of the angle of 750 degrees cuts the unit circle, respectively. So we already have 3 points, A, B, and C. What would the relation between these three endpoints be if all three angles were to be drawn on the same unit circle? It can be seen clearly that if this is 30 degrees, here we would get point A. For 390 degrees, here we would get point B. And finally, for 750 degrees, we would get point C respectively. Now, using the angles that had to be drawn in order to reach these points, determine their coordinates. Here, at this point, I should remind us of the use of a unit circle. So I'm going to draw a unit circle and I will remind us that given an angle theta on this and M being the endpoint, we used to say sort of what we called a poem on that. And that poem was like that. Since in order to get to point M, I had to draw an angle of theta degrees. The coordinates of M can be given as cosine of theta, comma, sine of theta. I will now apply this knowledge, this poem, for my three different points, which are basically the same point. For A, which relates to 30 degrees, I can say that since in order to get to point A, I had to draw an angle of 30 degrees, then the coordinates of A can be expressed as cosine 30, sine 30. Let's go to B, which is related to the angle of 390 degrees. And again, the poem will be the following. Since in order to get to point B, I had to draw an angle of 390 degrees, then the coordinates of B can be written as cosine 390, comma, sine 390. Finally, since in order to get to point B, I had to draw an angle of 750 degrees, the coordinates of C can be written as cosine 750 and sine 750. And what did I show before? I saw that A, B, and C are the same, and this means that all these three sets of coordinates basically describe the same point, which basically means that cosine 30 should be equal to cosine 390, should be equal to cosine 750, and the same thing should apply for the sines as well. Now, by combining our observations, these observations, what can we conclude? We did conclude that all cosines are the same, all sines are the same, sorry, and now we need to generalize this conclusion. To generalize that, let me write that again, and let me write that cosine of 30 is cosine 390 is cosine of 750. Now, I do notice that I can express cosine 390 as cosine 1 times 360 plus 30. And I can express cosine 750 as cosine of 2 times 360 plus 30. Also, I can express cosine 30 as cosine of 0 times 360 plus 30. So, it wouldn't be wrong if I generalized the following, that all of them would still be equal to the cosine of k times 360 plus 30, where k is an integer, 1, 2, 3, 4, 5, 6, and negative 1, negative 2, negative 3, negative 4, which is a whole number, and shows how many full circles we have drawn in order to go to that angle. And now, if we further generalize that without just using the angle of 30 degrees, we could conclude that cosine of k times 360 plus theta would be the same as cosine of theta. And similarly, the sine of k times 360 plus theta would have been equal to sine of theta. In words, we need to remember that trigonometric ratios of k times 360 plus theta are the same as the trigonometric ratios of theta. And that is the important part. Now, can you suggest a possible methodology that would allow you to find the trigonometric ratios of an angle greater than 360 based on this conclusion? Yes, certainly. We could say that given an angle greater than 360, 360, I should firstly divide it by 360 degrees. I don't necessarily need the exact division. I simply need its integer part. So if we end up with 2 point something, I just need that 2. Okay, because this would show the full circles that would be drawn. If, however, I want to do the full division, it's okay. If we divide that, we, let's say, either keep the integer part of this division, which is basically the quotient in our division, or just the remainder. And thirdly, continue with the remainder. And we'll do an example for that. Continue with the remainder the exact way you would normally do. Let's work an example to see what I mean by that. Find the trigonometric ratios of 1320 degrees, 1320 degrees. Obviously, it is an angle which is greater than 360 degrees. Now, we need to divide 1320 by 360. So basically, we need to do this division. When I was in your age, however, I didn't do it like that. I found it easier to just add. So I would go and say 360. Another 360 is 720. Another 720 is 1080. Another 360 is 1440. So 1320 is somewhere between, which means that I had to draw 3 circles, which means that 1320 should be equal to 3 times 360 plus something. So 1320 is equal to 1080 plus theta, and from here it is obvious that theta is 240. What does this mean? This means that 1320 has the same trig ratios as the angle of 240 degrees. So now we managed to find an equivalent way of acting. We just need the trigonometric ratios of 240. We have already seen how we are working on these cases. 240 is obviously on the third quadrant. Since it's on the third quadrant and I'm working with degrees, it can be written as 180 plus theta, which makes it obvious that theta should be 60 degrees. The coordinates of here, of that point, would have been cosine 60, sine 60. The coordinates on the third quadrant would have been cosine 240, sine 240. So I know that between these two quadrants, both x's and both y's are opposite. So that would have meant that cosine 240 is minus cosine 60, which is 1/2, so minus 1/2. And sine of 240 is minus sine of 60, which is minus square root of 3/2. So overall, we would say that the sine of 1320 degrees is primarily equal to the sine of 240 degrees, which is opposite to the sine of 60, which is minus square root of 3 over 2. The cosine is at first equal with cosine of 240, which is opposite to cosine of 60, which is equal to minus 1/2. Now, enough with degrees, let's continue with radians. What would be different if your angle was given in radians instead of degrees? Not much. The only difference, and let me write that here, the only difference would have been that instead of dividing by 360 degrees, I would divide by 2 pi. Let me see if I have an example. I don't have an example, so let's create an example right now. Just give me some 6 pi. 22 pi thirds. Okay, so example, find sine of 22 pi thirds. Okay, let's see the solution. First of all, obviously 22 pi over thirds to over 3 is greater than 2 pi. And I want to see how many full circles I have drawn. So I'm going to do 22 pi over 3 and all that divided by 2 pi. This can be written also as 22 pi thirds divided by 2 pi. I'm going to apply the keep, change, flip thing. So I'll keep 22 pi thirds multiplied by 1 over 2 pi. I'll now combine them into one fraction, 6 pi. Pi's are cancelled out. So I'm left with 22 over 6, which is roughly 3 point something. It's okay, I'll find that something later on, but this 3 for now means 3 circles. And 3 circles is the same as 3 times 2 pi. So 22 pi thirds is 3 times 2 pi plus theta. From here, we end up with 22 pi thirds minus 6 pi equals theta, which means that theta should be 4 pi thirds, which now means that the trig ratios of 22 pi thirds are the same as the trig ratios of 4 pi thirds. So I basically need to find those ones. Now, 4 pi thirds. I need to determine the quadrant first. Obviously, 4 pi thirds is greater than pi since 4 thirds is greater than 1. That angle being greater than pi means that we definitely reject the first two quadrants, and we could be either on the third or on the fourth. How can I see that? I can compare that with the natural boundary of these two quadrants, which is 3 pi over 2. So we have 3 pi over 2 here. We do some cross. 8 pi less than 9 pi. Whatever holds for these products holds for the fractions above them. So 4 pi thirds should be less than 3 pi over 2, which means that we should reject the fourth quadrant as well, and we are working on the third quadrant. Let me change color again. On the third quadrant now, And let me firstly give us some space here. And let's change the color. Now, we are on the third quadrant. The angles on the third quadrant are of the form in radians of pi plus theta, where theta is the corresponding angle on the first one. So, if pi plus theta is 4 pi thirds, this means that theta is 4 pi thirds minus pi, which means that it is equal to pi over 3, and that is an indicator that things are working well, because pi over 3 is one of the angles that should be known. So I'm having an angle of pi over 3. Let me create even more space. Sorry about that. So we are having the angle of pi over 3 here, which means that the coordinates of this point would have been cosine pi over 3, sine pi over 3, and also the 4 pi over 3 here, which means that the coordinates of this are cosine 4 pi over 3 and sine of 4 pi over 3. And we know that these two are opposites. So finally, remember that we simply needed to calculate the sine of that. Sine of 22 pi over 3, we firstly saw that this would be equal to sine of 4 pi over 3. But now in the end, we just saw that this should be the opposite of sine pi over 3, which is a known value. We know that sine of pi over 3 should be square root of 3 over 2. So that would have been negative square root of 3 over 2. And that is pretty much all. What we saw on this video is just an extension that allows us to calculate trigonometric ratios of angles which are greater than 360 degrees. Remember, we divide by 360, we keep the remainder. So we find the first equivalent angle, and by equivalent, I mean the first angle which lies on the unit circle, which is less than 360 degrees or 2 pi radians. And then from there, we want to connect it with an acute angle. Hopefully, this acute angle should be one of the known ones, and this is how we would proceed. I hope I made things easier. I want you to study over again the theory that we just saw. However, if you face difficulties, if you still have questions, if you need more clarification, please don't be shy. Leave your thoughts below the video in the comment area, and I'll make sure to respond back to you as soon as possible. As always, thank you for watching, and we'll see ourselves on another video. Have a good day.